Welcome to today's problem walkthrough. In this session, we'll tackle problem number 54, titled Spiral Matrix. This is a fascinating algorithmic challenge that involves traversing a matrix in a spiral pattern. Stay tuned as we break the problem down step by step and explore efficient approaches to solve it. Let's dive in. The problem we're solving is to traverse a 2D matrix in a spiral order and return all its elements as a single list. The spiral traversal starts at the top left corner and follows a clockwise pattern, moving right along the first row, then downward along the rightmost column, then left along the bottom row, and finally upward along the leftmost column. This process repeats while there are unvisited elements in the matrix. The input will be provided as a 2D integer array representing the matrix, and the output should be a list of integers in the spiral order that the traversal produces. For example, consider the matrix shown here with 3 rows and 3 columns. The traversal starts at the top left corner with the element 1. First, we move right across the first row, collecting 1, 2, 3. Then, we move downward along the rightmost column, collecting 6, 9. After that, we traverse left across the bottom row in reverse, collecting 8, 7. Next, we move upward along the leftmost column, adding 4. Finally, the center element 5 is visited. Combining all of these steps, the spiral order of this matrix is 1, 2, 3, 6, 9, 8, 7, 4, 5. Now, let's look at another example with a matrix that has 3 rows and 4 columns. The traversal begins at the top left corner with the element 1 and moves right across the first row, collecting 1, 2, 3, 4. Next, we move downward along the rightmost column, collecting 8, 12. Then, we traverse left across the bottom row in reverse, collecting 11, 10, 9. After that, we move upward along the leftmost column, adding 5. Finally, we traverse the remaining second row from left to right, collecting 6, 7. Putting it all together, the spiral order for this matrix is 1, 2, 3, 4, 8, 12, 11, 10, 9, 5, 6, 7. For a single element matrix, like 7, the spiral order is simply 7. The constraints for this problem ensure that the matrix dimensions, m and n, are between 1 and 10,000, and the values within the matrix range from -100 to 100. Additionally, there are a few edge cases to consider. If the matrix has only one row, the output will be the elements of that row in left to right order. If it has only one column, the output will be the elements of that column in top to bottom order. For an empty matrix, the output will be an empty list. Finally, single element matrices, like 5, will result in a single element list, 5. It's important to ensure the algorithm can handle very large matrices efficiently, given the constraints. To solve the spiral matrix problem, one approach we can consider is the brute force method, which involves manually simulating the spiral traversal of the matrix. The idea here is to process the matrix layer by layer. For each layer, we traverse the top row from left to right, then move down the rightmost column, followed by traversing the bottom row in reverse, and finally moving up the leftmost column. To achieve this, we define boundaries top, bottom, left, and right that shrink inward as we complete each layer. This process continues until every element in the matrix has been visited. The computational complexity of this approach is O, n*m, where n is the number of rows and m is the number of columns, as each element is visited exactly once. The space complexity is O(1), since we don't use any additional data structures apart from the result list. While this approach is straightforward and easy to implement, it requires careful handling of boundary adjustments, which can be error-prone if not managed properly. Another approach we can use is an optimized method that employs a directional simulation with explicit control. This method simplifies the traversal process by using a direction array to manage movement. Each direction, right, down, left, and up, is represented as a change in row and column indices. Starting at the top left corner of the matrix, we iterate through all the elements, using the direction array to guide movement. Boundaries are dynamically adjusted as we encounter edges or revisit cells to ensure that no element is processed more than once. This approach is efficient, with a time complexity of O, n*m, and uses constant space, O(1), since no additional storage is required beyond the result list. The use of direction arrays makes the logic more concise and reduces the chances of errors compared to manually managing boundaries. However, this method does introduce a slight increase in code complexity due to the use of direction arrays. The spiral matrix problem can also be solved recursively by peeling off one layer of the matrix at a time. The intuition here is to iteratively reduce the problem size by extracting the top row of the matrix and then recursively processing the remaining sub-matrix, which is rotated counterclockwise. This process continues until the base case is reached, specifically, when the matrix is empty, in which case an empty list is returned. The result for each layer is combined with the recursive result to form the final output. In terms of complexity, the time required is O(n*(m), as every element is visited exactly once. However, the space complexity is also O(n*(m), due to the additional stack space consumed by recursive calls. While this approach is elegant and concise, it's less practical for larger inputs because of the significant space overhead introduced by recursion. After considering multiple strategies, the optimized approach using directional simulation was chosen as the most effective solution for the spiral matrix problem. This method breaks down the traversal into sequential movements along 4 directions: right, down, left, and up, while dynamically adjusting boundaries to avoid revisiting elements. The use of a direction array simplifies the movement logic, making the implementation more intuitive and less error-prone. A key realization here was that combining boundary conditions with direction arrays eliminates the need for manual direction handling, resulting in a more robust solution. This approach is efficient, with a time complexity of O(n*(m) and operates in constant space, O(1), making it well suited for large matrices. Additionally, it avoids the pitfalls of recursion, such as stack overflow for large inputs. Compared to the brute force method, it is less prone to boundary adjustment errors, and while the recursive approach is elegant, its high space complexity makes it less practical. Overall, the optimized directional simulation approach represents the best balance of simplicity, efficiency, and scalability for this problem. To solve the spiral matrix problem, we need to traverse a 2D matrix in a clockwise spiral order, starting from the top left corner and moving layer by layer. The algorithm begins by defining 4 boundaries: top, which starts at 0 and tracks the first row of the unvisited portion; bottom, initialized as the last row index; left, initialized at 0 to track the first unvisited column; and right, set to the last column index. These boundaries help us define the current layer of the matrix as we traverse. Additionally, we'll create an empty list called result to store the elements in the order they are visited. With these boundaries and the result list, the algorithm proceeds layer by layer, continuing until the boundaries overlap, indicating that all elements have been visited. The traversal within each layer follows a systematic order. First, we move left to right across the top row, appending elements to the result list. After this, the top boundary is incremented by 1 to exclude the row we just processed. Next, we move top to bottom along the rightmost column, again appending elements to the result list. Once this is done, the right boundary is decremented by 1 to shrink the column. If rows remain, we then move right to left across the bottom row, appending these elements and decrementing the bottom boundary. Similarly, if columns remain, we move bottom to top along the leftmost column, appending elements and then incrementing the left boundary. This shrinking of the boundaries ensures that no element is visited more than once. Once all 4 directions have been traversed for the current layer, the algorithm checks the boundary conditions and continues to the next layer if possible. Finally, after all elements have been added to result, the list is returned. The spiral traversal naturally divides the matrix into layers, simplifying the logic. Each layer requires the same 4 directional traversals: across the top row, down the right column, across the bottom row, and up the left column. The boundaries, the top, bottom, left, and right variables, are key to managing this process. By shrinking these boundaries after each traversal, we ensure that the algorithm progresses inward layer by layer without revisiting any elements. This boundary management handles edge cases as well, such as when the matrix is a single row or column. In these cases, the boundaries quickly overlap, causing the loop to exit once all elements are processed. For an empty matrix, the loop doesn't execute because the initial boundary conditions are not satisfied. These mechanisms guarantee the algorithm's robustness and correctness. The algorithm uses 2 simple data structures: the boundaries and the result list. The boundaries, top, bottom, left, and right, are stored in 4 integer variables, which are efficient and require constant space. The result list accumulates the elements in the spiral order and requires space proportional to the number of elements in the matrix, which is O, n asterisk m. Analyzing complexity, the time complexity is also O, n asterisk m, because each element of the matrix is visited exactly once during the traversal. Since the algorithm doesn't perform redundant checks or unnecessary operations, it efficiently handles matrices of all sizes. Overall, the space complexity is dominated by the result list, making it O, n asterisk m, while the boundary variables contribute only a constant amount of space. To further optimize the algorithm, a couple of considerations are important. First, redundant checks can be avoided by ensuring that the conditions top equals bottom and left equals right are evaluated before each directional traversal. This prevents unnecessary computations when the boundaries have already overlapped. Additionally, a precheck for an empty matrix can save computation time by returning early when no elements are present. These optimizations streamline the algorithm and ensure it handles edge cases efficiently. Now, let's apply these concepts to an example traversal to see how the algorithm works step by step. Consider the input matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. We start with top equals 0, bottom equals 2, left equals 0, right equals 2, and an empty result list. First, we traverse the top row left to right, adding 1, 2, 3 to result in updating top to 1. Next, we traverse the right column top to bottom, adding 6, 9, and updating right to 1. Then, we traverse the bottom row right to left, adding 8, 7, and updating bottom to 1. Moving up the left column, we add 4 and update left to 1. Finally, we traverse the remaining top row left to right, adding 5 and updating top to 2. At this point, the boundaries overlap and the loop exits. The final result is 1, 2, 3, 6, 9, 8, 7, 4, 5, which represents the matrix elements in spiral order. Here, we are implementing the spiral order function, which takes a 2D matrix as input and returns its elements in a spiral order. First, we check if the matrix is empty or invalid by verifying if it exists and contains at least one row. If not, we return an empty list. Next, we initialize an empty list called result, which will store the spiral elements. We also define 4 boundary variables, top and bottom to represent the topmost and bottommost rows, and left and right to represent the leftmost and rightmost columns of the matrix. These boundaries will help us traverse the matrix layer by layer in a spiral fashion. The while loop ensures our traversal continues as long as the boundaries are valid, meaning the top index does not exceed the bottom index and the left index does not exceed the right index. Inside the loop, we start by traversing the top row from the left boundary to the right boundary and append each element to result. Once the top row is processed, we increment the top boundary to move inward. Then, we traverse the rightmost column from the top boundary to the bottom boundary, appending each element to result, and decrement the right boundary to shift inward. After this, we check if the top boundary is still within the bottom boundary. If it is, we proceed to traverse the bottom row from the right boundary back to the left boundary. After appending these elements, the bottom boundary is decrement to move inward. Next, we verify if the left boundary is still within the right boundary. If the left boundary is still valid, we traverse the leftmost column from the bottom boundary up to the top boundary, appending each element to result. After processing this column, we increment the left boundary to finalize the inward shift. This completes one full layer of the spiral traversal, and the loop continues if there are additional layers to process. Once all elements of the matrix have been added to result in spiral order, the function returns the result list. This step-by-step approach ensures that we traverse the matrix efficiently while maintaining the spiral pattern. This implementation is concise and leverages boundary adjustments to handle the traversal dynamically, layer by layer. Here, we start by defining the spiral order method, which takes a 2D array matrix as input and returns a list of integers representing the elements in spiral order. The first step is to handle edge cases where the matrix is null, empty, or has no columns. In such cases, we simply return an empty list. Next, we initialize some variables, result to store the final output, and 4 boundaries, top, bottom, left, and right to keep track of the current edges of the matrix as we traverse it. The while loop runs as long as the top boundary does not exceed the bottom and the left boundary does not exceed the right. Inside the loop, we first traverse from left to right along the top row, adding each element to the result. After that, we increment the top boundary to mark that the top row has been processed. Then, we move down along the right column, adding elements to the result and decrementing the right boundary once the column is complete. When the top boundary is still less than or equal to the bottom, we proceed to traverse from right to left along the bottom row, adding the elements in reverse order and decrementing the bottom boundary. Similarly, if the left boundary is still less than or equal to the right, we move upward along the left column, adding elements to the result and incrementing the left boundary. These steps ensure that we traverse the matrix layer by layer in a spiral pattern. Once all rows and columns are processed, the while loop exits, and we return the result list containing the elements in the desired order. This implementation efficiently handles the traversal by adjusting the boundaries dynamically, ensuring that each element is visited exactly once. To start, we are working with a small 2x2 matrix. The initial setup defines 4 boundaries, top and bottom to represent the first and last rows, and left and right for the first and last columns. The result array is initialized as empty. The traversal begins with the top row, moving left to right. Here, we append the elements at positions matrix 0, 0, and matrix 0, 1, which are 1 and 2, to the result array. After this step, the top boundary is increment to 1, effectively excluding the first row from further traversal. Next, we move to the right column, traversing from top to bottom. The only element here is matrix 1, 1, which is 4, and it gets added to the result. At this point, the right boundary is decrement to 0, narrowing the traversal area further. Now, we proceed to the bottom row, moving from right to left. Since the right and left boundaries are both 0, the only element to append is matrix 1, 0, which is 3. This updates the result array to 1, 2, 4, 3. The bottom boundary is then decrement to 0. At this stage, the exit condition is met because top is greater than bottom and left is greater than right. This means there are no more elements to traverse. The final output for this 2x2 matrix is 1, 2, 4, 3. With this example complete, we'll now look at a larger 3x4 rectangular matrix to see the same logic applied on a bigger scale. For this rectangular matrix, the initial setup defines the boundaries as top equals 0, bottom equals 2, left equals 0, and right equals 3, while the result array starts empty. The first step is traversing the top row from left to right. This means appending the elements 1, 2, 3, 4 to the result, which updates it to 1, 2, 3, 4. The top boundary is then increment to 1. Next is the right column, where we traverse downward and append the elements 8 and 12 from matrix 1, 3, and matrix 2, 3. This extends the result to 1, 2, 3, 4, 8, 12. The right boundary is decrement to 2, narrowing the traversal area. For the bottom row, we move right to left and append 11, 10, 9 from matrix 2, 2, matrix 2, 1, and matrix 2, 0. This updates the result to 1, 2, 3, 4, 8, 12, 11, 10, 9. Finally, the bottom boundary is decrement to 1, and we continue with the left column next. Now, we handle the left column, traversing upward. The only element here is 5 from matrix 1, 0, which gets appended to the result, making it 1, 2, 3, 4, 8, 12, 11, 10, 9, 5. The left boundary is increment to 1. Next, there is a remaining top row to traverse. Moving from left to right, we append 6 and 7 from matrix 1, 1, and matrix 1, 2, respectively. This finalizes the result as 1, 2, 3, 4, 8, 12, 11, 10, 9, 5, 6, 7. At this point, the exit condition is met because the top boundary has surpassed the bottom, and the left boundary has surpassed the right. No more elements remain to be traversed, so the final output for this matrix is 1, 2, 3, 4, 8, 12, 11, 10, 9, 5, 6, 7. Next, we'll examine a simpler case with a single row matrix. In the case of a single row matrix, the initial setup defines top equals 0, bottom equals 0, left equals 0, and right equals 4, while the result array starts empty. Since there is only one row, we traverse it directly from left to right. The elements 1, 2, 3, 4, 5 are appended to the result, updating it to 1, 2, 3, 4, 5. After this, the top boundary is increment to 1. At this point, the exit condition is satisfied because the top boundary has surpassed the bottom, and there are no other rows or columns to traverse. The final output for this matrix is 1, 2, 3, 4, 5. This demonstrates how the algorithm handles a straightforward case efficiently, completing the spiral order traversal in just one step. The time complexity of the spiral matrix algorithm is O, m*n, where m represents the number of rows and n the number of columns. This is because the algorithm traverses each element of the matrix exactly once. To achieve this, the traversal is performed in concentric layers. First, we process the top row from left to right, which involves iterating through all columns in the current top row. Next, we handle the rightmost column from top to bottom, iterating through the rows in that column. If there are still unvisited elements, we move to the bottom row and traverse it from right to left, followed by the leftmost column from bottom to top. Each of these steps processes some portion of the matrix, and since no element is revisited, the total number of operations corresponds directly to the total number of elements, which is m*n. Now, since each element of the matrix is visited exactly once during the traversal, the overall time complexity is directly proportional to the total number of elements, making it O, m*n. Next, let's consider the space complexity. Excluding the space needed for the output list, the algorithm uses only a constant amount of memory for variables like top, bottom, left, right, row, and col that keep track of the boundaries and indices. These variables require O(1) space. However, the output list result must store all m*n elements, which contributes O(m*n) space. Therefore, if we include the output list, the space complexity is O(m*n). Otherwise, the space complexity is considered O(1), since no additional data structures grow with the size of the matrix. When comparing this solution to a brute force approach, the difference becomes clear. A naive method might involve slicing rows and columns repeatedly to form the spiral order. For instance, you could extract the first row, then the last column, then the last row in reverse, and finally the first column in reverse, iteratively shrinking the matrix. However, this would require creating intermediate copies of the matrix or maintaining a modified version, which introduces an additional space overhead of O(m*n). While the time complexity would still be O(m*n), due to visiting each element, the memory usage would be significantly higher. In contrast, the optimized solution avoids these inefficiencies by using boundary markers like top, bottom, left, and right to control traversal, eliminating the need for intermediate copies. This reduces the space complexity to O(1), excluding the result list, making it far more memory efficient. Finally, let's analyze the best, average, and worst-case scenarios for this algorithm. Regardless of the shape or contents of the matrix, each element is visited exactly once. This consistent behavior means the time complexity remains O(m*n) in all cases. Similarly, the space complexity is constant at O(1) when excluding the result list, as the algorithm doesn't use any additional data structures that grow with the input size. Mathematically, we can prove the time complexity is O(m*n) by noting that the total number of elements is n equals m*n, and each is processed once without any nested loops dependent on the input size. The space complexity, dominated by the output list storing n elements, is O(m*n) when including result or O(1) otherwise. This balanced time and space efficiency make the algorithm robust across all scenarios. When solving the spiral matrix problem, a few common mistakes can arise if you're not careful. First, incorrect traversal boundaries are a frequent issue. This happens when you forget to update the top, bottom, left, or right boundaries after completing a layer of the traversal. The result can be that some elements are traversed multiple times or skipped entirely. To fix this, it's critical to adjust these boundaries systematically after processing each edge of the matrix. Another pitfall is infinite loops caused by improper while loop conditions. If, for example, you use while top bottom but don't also check left right, the loop may never terminate. A safer and more comprehensive condition is while top equals bottom and left equals right, which ensures the loop handles all edges appropriately and exits at the right time. Lastly, out-of-bounds errors can occur when you attempt to access indices that lie outside the matrix dimensions. This often results in runtime errors or crashes. To avoid this, always ensure that your indices stay within the current boundaries of the traversal. Careful attention to these details can save you from unnecessary debugging time and ensure your solution runs smoothly. Another challenge to watch for is the mismanagement of edge cases. For instance, single-row or single-column matrices can behave differently than larger ones. If these cases aren't handled properly, your solution may fail to produce the correct results. Testing matrices with dimensions like 1xn or nx1 thoroughly will help you catch and address these issues. Additionally, inefficiencies can arise when handling larger matrices. Using additional space unnecessarily or repeatedly iterating over the same elements can increase both time and space complexity. To optimize your approach, focus on in-place traversal techniques that minimize memory usage and eliminate redundant computations. By addressing these inefficiencies, you'll not only improve performance but also demonstrate a deeper understanding of the problem. To succeed in interviews, it's important to understand some key insights about the spiral matrix problem. Recognizing patterns is essential, as spiral traversal relies on dividing the matrix into layers or rings. Each layer involves a cycle of 4 directional movements, traversing the top row, the right column, the bottom row, and finally the left column. Managing boundaries correctly is another important skill, as interviewers often use this as a follow-up question to evaluate your understanding. They may also ask you to optimize for special cases, such as sparse or very large matrices, so be prepared to discuss trade-offs involving time and space complexity. Edge cases, like matrices with only one element, a single row, or a single column, should always be clarified up front. Interviewers often include follow-up variations as well, such as reversing the spiral order, skipping certain elements during traversal, or adapting the solution for non-square matrices. Mastering these aspects will help you stand out as a strong candidate. Beyond the spiral matrix problem itself, there are related challenges that build on similar concepts. For example, LeetCode 59 involves generating a spiral matrix rather than traversing one, while LeetCode 73 focuses on setting matrix zeros, another type of manipulation problem. LeetCode 498 introduces diagonal traversal, which is an alternative traversal pattern. Exploring these problems can provide a deeper understanding of matrix manipulation techniques. As for alternative approaches, one option is the recursive method, where you process one layer of the matrix at a time. While conceptually simpler, recursion can lead to stack overflow errors when working with very large matrices. Another approach is simulated path traversal, which uses a direction array to mimic movement through the matrix. This method requires extra bookkeeping to track visited cells, which increases space complexity. Each of these techniques has its own trade-offs, so understanding when to apply them is key. A third alternative approach is matrix flattening. In this method, you first convert the matrix into a one-dimensional array and then reorder the elements to simulate spiral traversal. While this approach may seem straightforward, it comes with a significant trade-off: high space complexity. Flattening a large matrix uses extra memory, which makes it inefficient for larger datasets. Because of this, matrix flattening is generally not preferred in scenarios where performance and resource optimization are critical. However, it can still be a useful conceptual exercise for understanding the mechanics of traversal patterns. By exploring these different approaches, you'll be better equipped to handle variations of the spiral matrix problem in interviews or real-world applications. Great job making it to the end. To summarize, we discussed the spiral traversal technique for matrices, focusing on an efficient iterative approach. Keep practicing similar matrix-based problems to strengthen your skills. Thanks again for watching, and don't forget to subscribe for more algorithm walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!